I'm Jordan. Michael Jordan. I'm Jordan. I'm Jordan. Michael Jordan.
In the first video of this lecture, we saw that starting from the invariant factor decomposition of a vector space V that has the structure of an f bracket x module, if we factored each of the invariant factors into a product of irreducible elements in f bracket x, and we were in the special case that the field F contains all of the eigenvalues of T, all of the roots of all of the invariant factors, then V is isomorphic to a direct sum of finitely many cyclic f bracket x modules of the form f bracket x mod the ideal generated by some linear polynomial to some power. So what are we going to do now? The idea is to choose a nice basis for this quotient vector space so that the matrix of the multiplication by x linear transformation on this quotient vector space acts in a particularly simple looking form. So this is just like what we did in choosing a basis for the quotient vector space f bracket x mod the ideal generated by ai of x when we were talking about rational canonical form and invariant factors. But the vector space basis we pick here is going to be a little different. So what we're going to do is consider the elements that are x minus lambda to the k minus 1, x minus lambda to the k minus 2, dot, 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 x minus lambda to the 1, and 1, which is x minus lambda to the 0. So I'm using this bar over the x. Why is that? Well, x is an element of f bracket x, and this bar x is the image of x in this quotient vector space under the natural projection homomorphism. So, okay, so we're going to look at these elements. And if you take, say, the first one and you expand it out, just expand everything out in terms of powers of this x bar, then you can write that as an f linear combination of the elements x to the k minus 1, x to the k minus 2, up to x and 1. And you can use that f linear combination to write down the coordinates as a column vector, where you take which elements of f give you this particular linear combination. And you can use those to make the columns of a matrix. And that is going to be the matrix relating these elements to this basis. So this is a triangular matrix with ones along the diagonal. So what does that mean? When you expand out x minus lambda to the k minus 1 as a linear combination of x to the k minus 1 down to x1, you have 1 times x to the k minus 1 plus some more complicated coefficients involving the lower order terms, the lower powers of x. So I say triangular here. The way that I just described it, where for each one of these elements, you get a column vector giving the linear combination of these basis elements, what you would get for the first one is 1 and then some other entries that are not 0. So I think that this matrix should be lower triangular, that it has ones along the diagonal, non-zero entries below those ones, and then zeros in the upper right corner. Tillman and Foote say that this is upper triangular. So maybe there's just some detail that I'm interpreting a little bit differently about how to go from these two sets of elements to this matrix. Either way, the point is the same. It's this triangular matrix with ones on the diagonal. And in particular, this matrix is invertible because it has determinant 1. Because if you have an upper or lower triangular matrix, the determinant is the product of those diagonal entries. So this is a change of basis matrix. Because this matrix is invertible, that means that you can write any one of these elements as an f linear combination of any one of these elements. We knew that because this is a basis. But you can also write any one of these elements as an f linear combination of any one of these elements, which means that this set is a basis for this vector space. Okay, So this is pretty close, actually, to something that we've seen earlier, exercise 3 in section 11.2. So I encourage you to check this out and look back at this exercise that we talked about. Okay, so now what are we going to do with this basis? This is our nice basis on which the multiplication by x linear transformation is going to have a particularly simple looking form. And this simple looking form is going to lead to the definition of the Jordan canonical form, just like the nice basis that we picked in the case where we had f bracket x mod the ideal generated by ai of x led to the definition of a companion matrix and rational canonical form. All right, so 2 little observations that are going to justify why this has a nice form. You can write x as lambda plus x minus lambda. Why is that a reasonable thing to do? Because everything here in our basis has to do with powers of x minus lambda. And what happens when you get x minus lambda to the k? Well, that's 0 in the quotient f bracket x mod the ideal generated by x minus lambda to the k. Right? This is clearly in this ideal, so this is 0 in this quotient. So maybe I should say it like this, actually, with the line. All right, so how does the multiplication by x linear transformation act on this vector space with respect to this basis? Well, you take x minus lambda to the k minus 1, multiply by x. That's the same as multiplying by lambda plus x minus lambda. So you get lambda times x minus k, x minus lambda to the k minus 1, plus 1 times x minus lambda to the k. But this is 0 in this quotient. So this is just lambda times x minus lambda to the k minus 1. What happens to our next basis element, x minus lambda to the k minus 2? Well, we get lambda times x minus lambda to the k minus 2 plus x minus lambda times x minus lambda to the k minus 2, which is 1 times x minus lambda to the k minus 1. Similarly, you get x minus lambda to the k minus 3 goes to lambda times x minus lambda to the k minus 3 plus 1 times x minus lambda to the k minus 2. X minus lambda to the 1 goes to lambda times x minus lambda to the 1 plus 1 times x minus lambda squared. 1 goes to lambda times 1 plus 1 times x minus lambda to the 1. So this is a description of how this linear transformation acts on this vector space in terms of this chosen basis. And now we can write down the matrix of this linear transformation with respect to this basis. And we'll see that it's almost a diagonal matrix. It isn't, but it's close. And this will lead to the definition of Jordan canonical form. We've chosen a basis for our quotient vector space so that the multiplication by x linear transformation acts in a particularly nice way. What does the matrix of that transformation with respect to this basis look like? It looks like this. So what's the first column? It's where does our first basis element get sent as an F linear combination of the other basis elements. And x minus lambda to the k minus 1 gets sent to lambda times x minus lambda to the k minus 1 here. So we just get lambda and then all zeros below it. X minus lambda to the k minus 2 gets sent to 1 times x minus lambda to the k minus 1 plus lambda times x minus lambda to the k minus 2. 1 lambda, zeros below. X minus lambda to the k minus 3 gets sent to 1 times x minus lambda to the k minus 2 plus lambda times x minus lambda to the k minus 3. 0, 1, lambda, zeros below. Continuing in this way, in the end, the very last one, 1 gets sent to lambda times 1 plus 1 times x minus lambda to the 1. So this matrix, where all of the blank entries are 0, this is the matrix of the multiplication by x linear transformation with respect to this basis. And this is really important. This gets a name. This is playing the same role that the companion matrix of the polynomial ai of x played when we talked about rational canonical form. So the k by k matrix with lambda along the main diagonal and 1 along the first super diagonal, the one right above the main diagonal. So main diagonal, first super diagonal. This is called the K by K elementary Jordan matrix with eigenvalue lambda. So K is giving the size of the matrix. Lambda is giving you the diagonal entry. Or this is also often called the Jordan block of size K with eigenvalue lambda. So what happens? In the elementary divisor decomposition of V, we have that V is isomorphic to f bracket x mod the ideal generated by x minus lambda 1 to the alpha 1 plus direct sum f bracket x mod the ideal generated by x minus lambda 2 to the alpha 2, and so on. So we're just going to apply this idea, choosing the vector space basis for this quotient that looks like this for each one of those cyclic factors in this elementary divisor decomposition. These elements are elements of these quotients, but since V is isomorphic to the direct sum of all of these quotients, each one of these elements in that quotient corresponds to some element of V under that isomorphism. So we're going to take the corresponding vector space basis of V. And now the matrix of the linear transformation T with respect to this basis will have a very nice form. It'll be a block diagonal matrix where our blocks are going to be these Jordan blocks. Just like for rational canonical form, we got a block diagonal matrix where each block was the companion matrix of the corresponding invariant factor. So I'll pause and erase, and I'll write that all here. The matrix of the linear transformation T with respect to this basis of V is a direct sum of Jordan blocks corresponding to the elementary divisors of V. We get a first Jordan block, a second Jordan block, up to a T Jordan block if we have these T different elementary divisors. So if we have the elementary divisor decomposition of V, that is V is isomorphic to f bracket x mod the ideal generated by x minus lambda 1 to the alpha 1, direct sum plus 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 x minus lambda t to the alpha t, so 1 for each of these blocks. This matrix is uniquely determined by that decomposition up to permutation of the blocks, because that elementary divisor decomposition of V doesn't come within order the same way that the invariant factor decomposition does, where a1 of x divides a2 of x divides a3 of x, and so on. So you can't just switch around your invariant factors in any which way. Like, they come with an order to them. So the elementary divisors don't. You can switch them around in any which way, and you're getting the same decomposition in a different order. So this matrix is uniquely determined, except maybe J1 isn't the first block. Maybe J2 is the first block. You write the J2 block first and then the J1 block next. It's not necessarily true that you should write the largest block first or the smallest block first. Maybe the more natural thing to do is group together all of the different blocks that correspond to the same eigenvalue lambda. Do like all of the blocks corresponding to one lambda, then all of the blocks corresponding to another lambda. But the important thing is that this matrix is it's uniquely defined up to permuting the order of the blocks that occur. All right, now I will pause and erase, and we'll give the definition of Jordan canonical form. We can now define Jordan canonical form. A matrix is in Jordan canonical form if it is a block diagonal matrix with Jordan blocks along the diagonal. And a Jordan canonical form for a linear transformation T is a matrix representing that linear transformation that is in Jordan canonical form. So these definitions are totally parallel to definitions for a rational canonical form, for a matrix, and for a linear transformation. And the next several results that we give will be completely parallel to results that we've given for the rational canonical form for a linear transformation, and then the rational canonical form for a matrix. So the theorem we'll state is the Jordan canonical form for linear transformations. And let's recall the setup. let's say that V is a finite dimensional vector space over a field F, and T is a linear transformation from V to itself. And remember, for this whole discussion, we want to assume that we're in the situation where F contains all the eigenvalues of T, so that all of the invariant factors of T factor into products of powers of linear polynomials. Okay, so under that assumption, 1, there exists a basis of V such that the matrix of T with respect to this basis is in Jordan canonical form. So we've already seen that. Where does that come from? Take the elementary divisor decomposition of V and choose this x minus lambda to the k minus 1, x minus lambda to the k minus 2, and so on, basis for each of the cyclic factors. The multiplication by x linear transformation is a Jordan block. The matrix of the multiplication by x linear transformation with respect to that basis is a Jordan block. We pick the corresponding basis of V, and what we get is a direct sum of those Jordan blocks for the matrix of T with respect to that basis. All right, so this is just like when we showed that a linear transformation T has a rational canonical form, that there exists a basis of V such that the matrix of T with respect to that basis is in rational canonical form. Part 2 is a uniqueness statement. The Jordan canonical form of T is unique up to permutation of the Jordan blocks along the diagonal. And this is just like the statement that the rational canonical form of a linear transformation is unique, except here we have a weaker notion of uniqueness because there's no order to the elementary divisors the way that there's an order to the invariant factors. So I think that the uniqueness for rational canonical form is not explained so clearly in Dummett and Foote, and that I should have said more when I was explaining this in that lecture. So I want to say a little bit about the idea for this uniqueness here. So the first thing I want to say is it's the same as the idea for uniqueness of rational canonical form. But what's the setup? So we know that there exists a basis of V for which the matrix of T is this block diagonal matrix where each of these blocks is a Jordan block. And where do these Jordan blocks come from? Each one corresponds to some elementary divisor of V. This is statement 1, gives us this. The procedure that we use to prove statement 1 gives us this, a basis of V for which the matrix of T is this matrix. So what we're going to do to prove uniqueness is suppose that there's some other basis of V for which the matrix of T is some other matrix in Jordan canonical form. And what we're going to need to show is that starting from this matrix, we are able to write V as a direct sum of finitely many cyclic f bracket x modules that look like f bracket x mod the ideal generated by x minus lambda I to the alpha I, and then by the uniqueness of the elementary divisor decomposition, that's going to say that these Jordan blocks are just a permutation of those Jordan blocks. Okay, so I'll pause and erase, and I'll write just a little bit more about the uniqueness argument here. So we have these two different bases of V, where the matrix of T with respect to the first basis is this one, the matrix of T with respect to the second basis is this one. So we're going to zoom in on this one. And we want to show that having the matrix of T be of this form gives V as a direct sum of T stable subspaces, one for each of these blocks, Ji prime, and that each one of these T stable subspaces is a cyclic f bracket x module with annihilator of the form x minus lambda to some power, where how do you go from a block to this x minus lambda to a power? The lambda comes from the diagonal entry along that block, and k is given by the size of that block. So this is really similar to what we did for rational canonical form. And let me say that the part of the rational canonical form uniqueness argument that I was not so happy with was this statement about the annihilator. So I don't think that I explained this well, and I talked about it in office hours, and there's something about it in the discussion board. But the idea was that if you have a T stable subspace and the matrix of T acting on that subspace is a block that looks like this, then we have a basis for this subspace. And by looking at the matrix of T, you can argue that you can get from that there exists one of those basis vectors so that you can get from that one to any one of the other ones by applying T several times. So just by looking at the form of the matrix, you can see that this is a cyclic f bracket x module. Well, what about this annihilator part? For the annihilator, what I found is that in the rational canonical form setting, the easiest thing to do is see that your annihilator gives some linear transformation on this subspace, and you want to show that the linear transformation that gives is the zero linear transformation on that subspace, on that cyclic f bracket x module. And one way to do that is by saying that the corresponding linear transformation sends every basis vector to 0. So we know the multiplication by x linear transformation has this nice matrix, this Jordan block. But what about the matrix corresponding to the linear transformation that is x minus lambda to the kth power? That seems like it should be more complicated, but really it's not so bad. So in the case of rational canonical form, what you can do is take the linear transformation corresponding to the companion matrix, to the polynomial defining your companion matrix, show that it sends the first of your basis vectors to 0. So that one just involves the definition of the polynomial. And then there's a little trick to see that it sends every other basis vector to 0 as well. And I don't want to go through the details here, but with that in mind, you can show that the annihilator in this case is this x minus lambda to the k, the ideal generated by this polynomial. So I'll leave that to you to think about it. But I think that it first would be helpful to go back and think a little bit about the corresponding argument for rational canonical form. All right, so I'm going to pause and erase. And then we've said what it means for a linear transformation to have a Jordan canonical form. Well, what about for a matrix? The last thing we'll do in this video is talk about Jordan canonical forms for matrices, just like we talked about Jordan canonical forms for linear transformations. And the idea is that these statements follow directly from the corresponding statements for linear transformations. So what's the setting? Let's say that A is an n by n matrix with entries in F, and we want to suppose that F contains all of the eigenvalues of A. So we know that A has a rational canonical form. It has a bunch of invariant factors. This is going to ensure that those invariant factors factor into products of powers of linear polynomials. So the first statement is that A is similar to some matrix in Jordan canonical form. And the second is that the Jordan canonical form of A, this matrix that A is similar to that's in Jordan canonical form, is unique up to a permutation of the Jordan blocks along the diagonal. And how do you prove these things? Well, we use this dictionary between linear transformations and matrices. So starting from your matrix A, you can let V be an n-dimensional vector space over F. And you can construct a linear transformation from V to itself by choosing a basis for V and then letting T act on a vector by sending it to this matrix A times the column vector of coordinates of your vector V expressed in that basis B. Then you know that T has a Jordan canonical form, that there exists a basis of V such that the matrix of T with respect to that basis is in Jordan canonical form. That matrix is similar to A. And then because the Jordan canonical form of T is unique up to a permutation of the Jordan blocks, the same type of statement exactly holds for the matrix A. So the way I think about proving these statements is to go through the statements for linear transformations, but you can state these results without any reference to the vector space V or the linear transformation T.